Good morning students. Welcome back to our online video class of chemistry. In previous section, we had started our new chapter, the solid state, and you have learned about some bases of solids. Today's class is about unit cell and different classification of unit cell and how to calculate the number of atoms present in the unit cell, close packing structures, and about voids. What is a unit cell? A unit cell is the smallest portion of a crystal lattice which repeated in different direction generates the entire lattice. A unit cell is characterized by 6 parameters. Now we are going to study how it is characterized. A unit cell is characterized by dimensions along 3 edges. The 3 edges are A, B and C. And the angles are alpha, beta and gamma. Here the angle between B and C is considered as alpha and the angle between A and C is beta and the angle between A and B is gamma. From this we can say a unit cell is characterized by 6 parameters, that is A, B, C, alpha, beta and gamma. Unit cell is broadly classified as primitive unit cell and centered unit cell. If the constant particles present only at the corner position of the unit cell, it is called primitive unit cell. And in the case of centered unit cell, the constant particles occupy other position also besides the corners. Centered unit cells are classified as body-centered cubic unit cell, face-centered cubic unit cell and end-centered cubic unit cell. In symbol of primitive cubic lattice, the points are only present at its corners. How many corners are there in a cube? There are 8 corners. So in primitive cubic lattice, the points are present only at the corners of each unit cell. Corners of each unit cell. Body-centered cubic lattice. In the case of body-centered cubic lattice, the points are present at the corners as well as at the center of the body of the cube. The points are present at the 8 corners of the cube. As well as at the center of the body of each cube. Next is face-centered cubic lattice. We have seen in primitive cubic lattice, the points are present at the 8 corners of the cube. In this case, the points are present at the corners as well as at the center of 6 faces of the cube. How many faces are there in a cube? 6 faces. So, in face-centered cubic lattice, the points are present at the corners, 8 corners. As well as at the center of 6 faces of the cube. One will present at here. Here. We have learnt A unit cell can be characterized by 6 parameters. Is it? On the basis of this, total 7 types of primitive unit cells are possible. The primitive unit cells show variation in the form of centered unit cells. The total number of possible unit cells in 3-dimensional lattice is 14. This is called Brevis lattice. The details of the lattice structure is shown in the picture. The total 7 types of primitive unit cells and the relation between sides and angles are given in the table. The 7 primitive unit cells are cubic, orthorhombic, tetragonal, monoclinic, triclinic, hexagonal and rhombohedral. Next, we are going to study about how to calculate the number of atoms in unit cell. Now we are going to calculate number of atoms present in primitive cubic unit cell. We have learned in primitive cubic unit cell, the atoms are present at the corners, 8 corners of the cube. Is it? Then each atom at this corner is shared between 8 adjacent unit cells. That is shown in this figure. I have told you each atom at the corner is shared between 8 adjacent unit cells. 4 unit cells in the same layer. 4 unit cells in the same layer and 4 to the upper layer. Therefore, only 1/18 of an atom actually belonging to particular unit cell. So, the total number of atoms in one unit cell is 8 into 1/8 equal to 1. Next is the calculation of number of atoms present in body-centered cubic lattice or BCC unit cell. In BCC unit cell, 8 atoms are present at corners as well as at the center. This is shown in the figure. 8 atoms are present at the corners as well as at the center. Is it? So, at each corners only 1/8 of the atom is within the unit cell. Thus, the contribution of 8 corners is 1/8 into 8. That is equal to 1. And there is one atom present in the center. Therefore, the total number of atoms present per unit cell is 1 plus 1, that is 2. From this we can say, in the case of body-centered cubic lattice, the number of atoms present per unit cell is 2. Number of atoms present in the face-centered cubic lattice or FCC cell. We know that a face-centered cubic cell contains atoms at the corners as well as at the center of 6 faces of the cube. The atom present at the face center is shared between 2 adjacent unit cells. We have learned about unit cell. What is a unit cell? A unit cell is the smallest portion of crystal lattice which repeated in different direction generates the entire lattice. So, adjacent to this unit cell, there are another unit cell are present. So, we can say the atom present at the center of the face shared between 2 adjacent unit cells, and only half of each atom belonging to an individual cell. Then the calculation becomes the number of atoms in unit FCC cell equal to 8 corners into 1 by 8 per corner of atom equal to 8 into 1 by 8 equal to 1. And 6 face-centered atom into half atom per unit cell equal to 3. Therefore, the total number of atom present unit cell equal to 1 plus 3 equal 4. The number of atoms per unit cell in primitive unit cell is 1 and body-centered cubic lattice is 2 and face-centered cubic lattice is 4. In solids, the constituent particles are close packed, leaving the minimum vacant space. Let us consider the constituent particles as identical sphere and build up three-dimensional structure in 3 steps. Close packing in 1 dimension. There is only one way of arranging spheres in 1-dimensional close packed structure, that is to arrange them in row and touching each other. In this arrangement, each sphere is in contact with the 2 of its neighbors and its coordination number is 2. What is meant by coordination number here? A coordination number is defined as the number of nearest neighboring particle. If you take the sphere, you can see adjacent to this there are 2 spheres are present. So, here the coordination number is 2. Close packing in 2 dimension. There are 2 possible ways to arrange sphere in 2 dimension. First one is square close packing. Sphere in the first row are exactly aligned with the second row. In this type of arrangement, each sphere is in contact with the 4 other spheres. Each sphere is in contact with the 4 other spheres. Hence, the coordination number here is 4. The 4 other spheres that are in direct contact of the central sphere is known as nearest neighbor. Since each layer is exactly same, this type is known as AA type. Second one is hexagonal close packing. If second row sphere are placed above the first row in a staggered manner in such a way that spheres are fit in depression of first row. You can see in the picture. Here the spheres are fit in the depression of first row. In this type of arrangement, each sphere is in contact with the 6 other spheres. Hence, the coordination number here is 6. The second layer is not exactly aligned with the first layer. Hence, this type of close packing is called AB type. The centers of 6 spheres are at corners of a regular hexagon. Hence, this packing is also called 2-dimension hexagonal closed packing. Close packing in 3 dimension. This packing can be obtained by putting 2-dimensional layer one above the other. 3-dimensional close packing from 2-dimensional square packed layer, that is AA type, is shown in this figure. If the arrangement of spheres in the first layer is called A type, then this lattice has AA type arrangement because all layers have same arrangement. Next is the 3-dimensional close packing from 2-dimensional hexagonal close packed layers. Let us take 2-dimensional hexagonal close packed layer A. place a similar layer above it such that the sphere of second layer are placed in depressions of the first layer. All the triangular voids of first layer are not converted by sphere of second layer. I hope you have understood what we learned today. We learned today about different types of unit cell and calculation of number of atoms in unit cell and closed packed structure.